Hey guys, so today we'll be solving this problem called find minimum diameter after merging two trees. In this problem, let's read it first. There exist two undirected trees with n and m nodes numbered from 0 to n minus 1 and from 0 to m minus 1 respectively. You are given two 2D integer arrays, edges 1 and edges 2, of length n minus 1 and n minus 1 respectively, where edges 1, ai, bi indicates that there is an edge between ai and bi in the first tree. Edges 2 of I, ui, and vi indicates that there is an edge between ui and vi in the second tree. You must connect one node from the first tree with another node from the second tree with an edge and return the minimum possible diameter of the resulting tree. The diameter of the tree is the length of the longest path between any two nodes in the tree. So we've been given two trees, tree 1, tree 2, and we need to connect two nodes from both of the trees such that we get the minimum possible diameter of the resulting tree. So how we can solve this problem is, first of all, we'll need the diameter. So we'll need the diameter of tree 1, we'll need the diameter of tree 2. And the second step is that we need to combine the diameter, or find the nodes which will combine the diameter and resulting diameter. We need to return that such that it is the minimum possible diameter of the resulting tree. So first of all, let's try to think about an approach. Um, so first we have this first tree, 0, 3, 2, 1, and the second tree is 0 and 1. So there is an approach by which we can solve this problem. Is one is topological sorting. So topological sorting, we'll be treating both of these as a graph, and topological sorting gives the order in which like the sorting gives an answer which is topological sorted form, which is like one action gets done and then the next action gets done depending on the dependencies that it has. So first is the one which is having the lowest dependency, and then the second is the highest dependency, and then so on. So that's the idea. Um, let's see how we can apply this in this problem, right? So actually we need to treat this as a graph, right? So we'll have this directed double-edged edges. So first of all, obviously, like we'll need to create a adjacency list. So we have 0, and 0 has 1, 2, 3, right? So 1, 2, and 3. 1 has 0 in it, 2 has 0 in it, and 3 has 0 in it, right? 0, 1, similar. So that's for tree 1, and this is for tree 2, right? So 0, 1, and 1, 0, right? So that's the adjacency list. If we want to create degrees, so in topological sorting, we need to create degrees in it, degrees of each node. So this is actually 3 degree because there are three dependencies or to it. This is 1, this is 1, this is 1. Similarly, this is 1 and this is 1, right? So in topological sorting, we actually create a queue. What do we do is we create a queue. We push uh, the ones which are having like the lowest degree, more specifically degree equal to 1. We push all of them in the queue and we pop it out one by one until and reduce the degrees of each because they are they are considered. And from there we move to the next node, or like the level, you can say. So yeah, going from lower dependency to higher dependencies. So that's the idea. Like once, so in this we will get, like if we do a topological sorting, we will get the answer as 1 because that's the level like that is considered. We'll keep a count and count the levels on it. From there we have the levels. We have how many, like what is the diameter. So diameter can be found easily between these two trees via the topological sorting. And then we can all combine the both two diameters, and also like we can consider each tree's diameter and see like what is the maximum between them and return that value. So that is a basic intuition of this problem. Let's get to the coding part in order to understand this better. Let's get to the coding part. First is we'll maintain edges. right? Which is basically storing the size of the two edges, or like two, you know, trees that we've been given. As I said, we'll create an adjacency list first. So yeah, that will give us the adjacency list. Let's actually create a function for making that adjacency list. So this function, make adjacency list, will actually store the edges in it, and also the size, right? So inside it, we'll store that, and moving forward, we'll continue to add stuff in it. So right now, we need to return a vector of vector. So I'll add that here, and yeah, it will be of size, right? So, right. And then I'll iterate through the edges, right? In edges, and I'll keep on pushing it to the adjacency list. So adjacency list edge of 0 dot pushback edge of 1, right? And yeah, same stuff here again, right? And then we return adjacency list from there. Once that's done, we'll find the diameter, find diameter, and pass values of size n. And also, like, we'll find the diameter of the second tree. The find diameter function will give that to us, right? Okay. Once that's done, we know that we have diameters of two trees, and we also need to combine it, because once we join two nodes of the two trees, we need to know the combined diameter, right? So combined diameter would be diameter 1, 2.0, plus seal of diameter 2, 2.0, and plus 1, right? That's the idea. And we return the combined diameter from there, right? Okay. Once that's done, let's get to the find diameter. So find diameter would be a function which is going to be like a topological sorting, as I said, to get the diameter value. Okay, one more thing that I missed to tell you is that combined diameter, uh, why are we doing this part, right? So this part is being done because it so diameter is combined by two nodes, like two farther away nodes in that tree, and the distance between them, right? So because we are actually combining with another tree, so we'll only use the half of the distance, right? So half of the distance is used there, and then yeah, similar for the second tree as well. We'll use half of the distance and add one to it, and then return the combined diameter. Uh, like yeah, also, this is wrong. We will return the max of the combined diameter, or diameter 1 or diameter 2, right? So it can be that one of them is 0, and we'll have to return the maximum value possible between them, which is also, you know, uh, like correct, because yeah, we are returning the diameter between, yeah, these three. So yeah, once that's done, let's get to the topological sorting part. So topological sorting, we have find diameter function, where we'll have the adjacency list and also n, right? And going forward from here, we'll have q, leaves of q, vector int, and degrees of n, right? Here we'll iterate through the array. We'll iterate through the adjacency list, as we need to store the degree. As I told you, like we first of all process the ones which are having the least amount of degree, right? So degrees of I equal to list of I dot size, right? uh, yeah, it will be basically the number of elements which are, or nodes which are actually dependent on that particular node, on the source node, and we'll store that in as a size. It will be as a size, right? So 0 is corresponding to 1, 2, 3, and basically because 1, 2, 3 are dependent on 0, so it has three dependencies, and that's why the degree is 3. So yeah, if degrees of I equal to 1, we'll be pushing it to the leaves queue. So that's the topological sorting rule that will start from there. So after that, we'll get to the queue part, or like how we'll process the queue and remove elements from the adjacency and so on. So yeah, in remaining nodes is currently n, and into layers, uh, leaves layers removed is equal to 0. So these two variables will be, so one is for maintaining that there are only if there are only two nodes which are left in the tree, we should come out of the while loop and yeah, return the value or answer. Leaves layers removed is the one which is basically denoting the diameter. So yeah, let's get, so first of all, remaining node should be greater than 2. So this is indicating that we always should be having more than two nodes in the tree, so that that can be joined with the other one. So in leaves queue dot size, right? So that's the size of the queue, and we have remaining nodes, uh, which will basically keep on decreasing as we process the tree, and also leaves layers removed plus plus, that's the one which is storing the diameter, right? And then we just iterate through the size I plus plus, and in current node equal to leaves queue dot front and leaves queue dot top, right? And yeah, from here we'll have int neighbor. This is the list of current node, right? That's the one which are popping out. We are popping out from the queue, and yeah, degrees of neighbor will be minus minus. That's the standard topological sorting algorithm. And if degrees of neighbor equal to 1, then we do leaves queue not push neighbor, right? Done. After this, yeah, after this we have next step, which is if remaining nodes are there, right? So if remaining nodes equal to 2, which is like two of them are left, then we actually return 2 into leaves layers removed plus 1, and otherwise we just return 2 into leaves layers removed, right? So what's this is that we had one layer which is this one, and then this is the second layer. So one was removed, right? So one was removed, which means that between, like, to find the diameter, so diameter is distance between two nodes, right? So it's multiplying by 2. So this is size 1 and this is size 1. So between, because that's the level which is removed, and still we are actually having more than two remaining nodes, or even lesser than that, then we will multiply it by 2 and return that. So yeah, that's the idea. That's the code. Let's run it to see if everything is working fine. Yes, so degrees of I equal to 1, Expected promotion. Okay, yeah. Right. So this one is missing the. Hmm, yes. That works. That's something. Good. I hope you guys understood and thank you.